Hello again, friends. So, I was thinking about how could we do an episode on lists, and that deleted itself. I figured the best way to do this is to re-implement common functions that are illustrative of how lists work in the Data.List module. That's kind of the typical way to do things anyways, but I guess the value add that I can do here is just trying to explain what exactly I'm doing and what my thinking is, because this is starting to get into, recursion. And the reason this is getting into recursion largely deals with the fact that we have a recursive data structure. So I can't imagine a case in which we, aside from some sort of counter with num, where we're recursing, for example, length, I guess would be a great example of where we're, even then, actually, no, we're just recursing on a data structure. I'm not sure. Maybe there is a case where we would need recursion without lists, but the two kind of go hand in hand. Even, if you look at, for example, this is now kind of getting a little out of bounds of the lesson, but if we look at tree and a rows tree implementation in Haskell, you can see it's nothing more. Well, not nothing more. It uses a list to build a forest. And a forest is just defined as a list of trees. And so I would go as far as to say that almost every single time we're using recursion, there's probably a list involved. And now, why is that? Well, you might have seen my Hangman video, so this is kind of old news, but the actual data structure of a list is defined as this guy here. So we got... And so, another way we could write this even, we could write this two different ways, but I'm sure from the one you'll see the other. So I made this to look more like the head of the data declaration. Now, of course, in the data declaration, I suppose I could, also do this instead, but I think you get the idea that really it's just a prettification, making it pretty for Haskell to show it as such. You also can't really find the list data structure on Google. At least I've been unsuccessful with that. You could probably go through the base package and find it. Actually, you definitely can, come to think of it. But, and so what's evident here, especially when we go like this, is that we have a recursive data structure. So a recursive data structure, in essence, is a data structure that is defined in terms of itself. So this is kind of where recursion ends, is when we have an empty list. But of course, you might recall that the only other case besides an empty list is a non-empty list. And so we can kind of continually substitute and have a, kind of expand this out where we'd have something like this. And what is the logic behind how we can do that? The logic behind how we can do that is that we're saying construct. So this list in this sense here is a type constructor, meaning it is creating a type. As you recall from the kinds episode, that there is no such thing as. So I'm just trying to put a timer on myself so that I can keep track of how long this video is. But as you might recall from the kinds video, a higher kinded type that is not fully applied. So for example, if I had just that, then the kind of a list would be not a real type, but expecting one more type argument in order for itself to become a real type. So if I check, let's put int here. So list of int is of kind singular star. And it'd be the same thing if I did that. It's just different ways of writing it. This is kind of more like if it was a, for example, maybe. But it's nicer to think or to view it in that way. So what this means here is that we could effectively substitute and say that what's inside the brackets here, we either delete it, delete it mentally, in the sense that we have to evaluate what its possibilities are. So when we have this, all it's saying is that there are two possibilities for what can happen inside this bracket. We either have an empty list, or we have this again. So we do, and then, so, and then, we could, now we're back to the same question of what does this evaluate to? We could continue to eliminate it mentally and substitute it out until we eventually get to the point of this. And so this being, in this sense, and I know it's a little confusing, this is probably might be the first time you're seeing a recursive data structure, but what is allowed with with data constructors, this guy, and then type constructors is that they can be the same name. So for example, let's change this to list, and we're gonna say list. It would be the same as if we started like this. And so that might be a little bit easier to think about, where we really have two data constructors, this cons operator and list, which takes no arguments. And I hope it's, did I say data constructors? I meant data constructors. I hope it said data constructors. Blah, blah, blah. So yeah, and that's why we are able to craft a recursive data structure. I'm not sure how a list would be defined in Python or any of that, but I do not care. But this is how it works in Haskell. So let me just eliminate that, and I'm going to comment this out so it doesn't bug me. And yeah, so and that is why we need recursion, because we're dealing with a recursive data structure. It's just, a well-fitted solution, I suppose. So, I'm going to start with this function here, and we're just going to work our way to the right, and that should be the contents of the video. I can't think of what else we would need to go over. Sure, one random thing will come to mind, but yeah. So we're going to implement this function here. I'm going to forget about the infix operator for now, because I have not used that in a long time, and you don't really need to, but yeah. So I'm going to recall this plusy. Yeah. Actually, let's just call, concat is a real thing. I'm going to call it put together. So, no, you know what? If I do this, this is going to work. Import prelude, hiding. So I need to, just a small note here, I need to put another set of brackets, since this is a special character for the function. Like it's not, called concat or whatever. It's like the plus sign. And then I'm going to say language. You don't really need to know exactly what I'm doing here. This is not so much important as to just, set up this video. And you can avoid doing this by just calling a different function. But I am, just going to do this. Sorry. So, this takes two lists and makes them into one full list. And so how you actually do this, so this is just, again, putting 2 and 2 together. If we were to say 1 to 5 plus 6 to 10, we would end up with 1 to 10. It's just putting the 2 together. List 1, list 2, and then how are we going to do this? So this one I think will probably be the most surprising of all, just in terms of it might look weird and it might be like, well, you didn't do anything there. But I guess, so maybe a good point to make here that is especially prevalent with lists. And oh my gosh, this is a perfect time for this. I haven't really talked about lazy evaluation too much. So Haskell is like 100% lazy in its evaluation. And I kind of think that it's lazy in its data structures as well. And it's obviously also lazy in terms of its functions. So a great example of this is a function which I didn't plan on covering today, but is perfect for this example. So let's say we had in JavaScript or any other language, I want to take 5 from an infinite list. So this here builds an infinite list, and this is going to take 5. And in JavaScript, how this would operate is that we would build the list, build the structure, and then we would run the function. However, when you think about it, why do we need, if we're only going to build, or if we're only going to take 5 from the list, we are never going to even use, or, we don't need anything past 5, past the first 5 elements of the list. And so, making, index number 1,000,001 is not going to help us at all. But JavaScript and other object-oriented languages will still do that. Here with Haskell, we don't need to do that, because what's going to happen, and see that was lightning fast, did not just, Haskell's not so fast that it just created an infinite list. Somehow, the list would never terminate, and so it wouldn't be necessarily a matter of fast, so much as maybe patience, I don't know. So this is going to lazily evaluate, in that it's going to see, does it have to continue going through this list? So it's going to keep peeling off from the list until the function is done. So take, if we were to evaluate take, we would slowly be decrementing from the 5. So, we would peel off 1 and we say, okay, take 4 from the rest of the list, take 3 from the rest of the list, take 2, take 1, take 0. And take 0 would terminate because, there's nothing more to take. And so that taking would force the next element in the list to be generated. So this is really helpful. I actually have a function in web scraping which generates all possibilities of a form, for instance, and because it's a generator, this function, if I run the function and just want to, I demand that the entire list be generated. My computer cannot handle the memory that it takes, because it's like literally, millions of permutations that are possible. So, but I don't actually need all million possibilities. I just need the next one for my web scraping. And so same thing here is with take. We're just effectively demanding a certain amount of work from a generator. Yeah. So why did we get on that? How the heck did we end up there? I have no. Oh yeah, laziness. So that's why we kind of have to do this. And I'm gonna call this L from L1, and we're gonna peel off L from L1. We're not gonna touch 2. And okay, so. Oh, yes. And so, yeah. So we just want to say... So this might just even look weird too, but what we're doing here is we are recursing. And so this is it. We have, besides... besides this last part here, where if we have an empty L1... then we just say you know what, I'm going to cheat, and I forget what they did in this case. I'm literally just copying from it's literally just Y's or L2. So I'm to be clear, I'm literally just copying from Prelude, at least for this one. I don't think I will need to for the other ones. That would be kind of fall down on my part. But I haven't thought about concat in a while, and other excuses I'm sure I could bring up. But yeah. So all we are doing here is we are effectively just laying out. I kind of think of it as laying out L1, and then. So eventually, in the last case, this is going to terminate to be just L2. So, again, with lists, all that's really required here is that the last placement has to be the empty list. So we could have, 1, 2, 3, 4, 5, etc., 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 and get all the way up to 1,000. And if we were to end here, then we would it would not know what this is. It would not compile, and that's because it's not yet a real type. It's still asking how it's going to evaluate. And so if we had this, then of course it will work. Yeah. And so that's obviously independent of the length of the list. And yeah, I don't think there's anything more to say about that besides, and well, that's really why this L2 here works, is because we are just laying out. So let's say we have 1 to 4 as the start of our list. What we're going to say is, so the last thing that we're going to do before we are done with our list is that we are going to end off with a colon, and then it's going to evaluate. This is going to turn into this statement here. And so if that list is from 5 to 8, it would look like this. And because this is a real list, we can really just take away the brackets. They're just more for eyesight. We will end up with this. So, yeah. I think that's exhaustion of that there. So length, I also like I like length because it's kind of a fun, easy function to build. So length takes a list of some length and gives us an int. And so this is also just really easy to do. So what we are doing here, we are going to say, so we actually don't even need to worry about the value of x. We just need to simply peel it off. And so it's fun because we're just going to do 1 plus length of x's. And let me think. So if this is an empty list, so I guess we've already peeled off everything, and now there's no point in adding any more, so we're just going to do 0. I'm just going to call this length prime. So I import, I gotta go back to main, import lists. Cool. And that compiles. So if I try out my function of length just to see that it works. Cool. It does work. That was pretty easy. And so all we're doing here, we're just recursing, and we have 1 here because that's representing the length of the list. And we're kind of doing this, recursively slash, I guess, statelessly, in the sense that we are just building an expression out. So this is going to continue to evaluate to 1 plus 1 plus 1 plus 1, and at some point plus 0. And we just build our recursive function so that it can figure out how many times it needs to add 1. Also pretty simple to do. And so this is another kind of fun function to me. And is so and takes a list of A and returns a bool. So what and is saying is that are all of these elements true? Yes or no? Am I? Oh yeah, right. This makes more sense. So x's. So I'm just going to do my syntax to peel off from the list. And I think I kind of neglected to explain that because I'm kind of thinking, I'm assuming everyone has watched Hangman, but that's not really a realistic assumption. I do definitely recommend it, but the reason we're able to do this pattern matching syntax just goes back to the list data declaration. And so we are just pattern matching on the data constructor of the cons. The same way that if we have data puzzle equals puzzle with an int, which it had more in the actual video, I could have a function which unwraps puzzle to find some int. So that would bring some int into the equation, which I could just return. Maybe I could add it together with something else. And yeah, so that's all we're doing is we're just pattern matching on the data constructor of the data type that we are working with. In this case, a list. So just to, what's the word I'm looking for? Go over the top with explaining it. Because we can pattern match here, and a list is a recursive data structure, we could continue to ask what's in the list, and we could just do this forever. I could make this pattern match, a billion long, and maybe maybe the compiler would fail at that point, but I doubt it. Even then, maybe it have to cause a memory issue, but I don't know. But this is not going to be likely very useful. It's logically better to just peel off one at a time. At least in this case, you might have some weird cases where it's like you want to match on, let's say, the last two elements of the list, and so yeah, but but by having these two pattern matched on, we have all of the patterns that are possible of that data type matched on our function. And so there's, assuming we've done this, we built our function properly, there's no way that we can get like a case not caught error, or I forget what it's actually called. It's like the missing case exception. Yeah. So here, how do we handle this? This is actually really simple. We're just simply saying, I thought this was going to be a little bit more interesting than I remember. There was another function that, whatever. We're really just saying this. So why this is going to work here is we are just recursing through, and we have two possibilities for what x can be, given that it is a bool. And if we look at the data structure, we can see why that's true. I don't think we need to with bool, but in general, we can think this through in this way. So I can see from bool, from the data declaration and nothing else, assuming I've never heard of Boolean before, that there are only two cases. And so if I have a set of pattern matches that describe the full possibility set, then I have pattern match on all cases. Wow, that sounded almost jargony-ish, but that's what we're trying to do, right? We for any function where we are taking in a data structure, which is, I guess, really every function, maybe not every, every function which takes an argument, I will say. I guess you could call IO actions a function of sorts, but they're not really a function. They're more of a statement or expression, rather. So if we have a function which takes at least one argument, then we need to make sure that we are pattern matching on all of the different cases of that given input type. And that's it's easy and doable to make sure we are pattern matching on all possible cases of input because we have a defined input type. And so with complex types even, we have a little bit more complexity, but there's only so many, with a complex type like a list, we just know that we have a repeating, case, basically, of either true or false. And so in this case, x is going to be either true or false, and the goal of this function is to ask if all of the elements in the list are true, but, and so with that said, if we have true, and then the next one evaluates to, being false, then true and false is false by logical rules, and so it could also be the case here that we get true and true. and then we get true and true and true and true and true and true and true, and then we get to the last element in the list, and the last element in the list, not talking about this because that's the end of the list, empty list, which we still need to just think about and handle. But let's say the last element in the list is false, then this will automatically, no matter what happened before it, become false. So yeah. Then in this case, what would we do? So this is an interesting kind of end case. What we want to do here is just basically not affect the previous results. If we, going through enumerating through the possibilities of what we could say here, if we said false, then we would always get false. Like we said, how the last element of the list being false, it would not matter what came before it, we would still get, false. Same thing would happen here if we just said that it is false here. So we're just going to say true because it will do nothing. So do that again, and that's fair. Let's go and do that, and do that, and do that. There we go. If we say and true, true. Oh. Okay, well, give me 1 second. I'm just going to do something here. Stupid thing. There we are. And if we say and, we get true. If we do false, we do get false. And now no matter what comes after, we are still going to get false. If we were to say and, well, I guess we would in this case get true, which is a bit weird. Yeah, but I guess that's how it's implemented. Now, if we go to the next one, product, also kind of simple, and you kind of the point I want to get across with this is just that you kind of notice some patterns, and because I think recursion in Haskell is really simple compared to what I imagine with other languages, just simply because, and I can't really say that for sure. I'm definitely no expert in, say, C#, for example, but with this being constrained to a singular case, then it becomes a lot easier to think about what to do at each step. And I can't imagine thinking about recursion with multiple different types in a heterogeneous list. And actually, that's another point I should have mentioned earlier, that these are in Haskell, lists are homogeneous, and that there's only one type in the function, in the list itself. We cannot have one and then a character, a string here, because it's homogeneous. And here it's giving a type error saying that it found a 1, so it's expecting a 1, and then it gets a string, which doesn't make any sense to it. So product, we're going to make a product here. Product, so this will work for anything with a num instance. Yeah, I guess it doesn't matter. Product, we are just going to, again, peel off from x's. And this is very similar to length in a way. Again, the pattern starts to emerge about how to do recursion and working with lists. We're literally just peeling off and then saying, continue recursing and placing in place. Right, so we're going to have x2 becomes here, and then x3, and then all the way up to xn, where n is the length of the list. Oh, geez, what is with me today? And we get to the end of the list. And well, how do we do this? We can't. If we were to multiply by 0, just starting with the wrong cases first, then it would not matter what is in our list. We would always just get 0. 2. I don't know what the point of sorry. I don't know what the point of that result would be. And so 1, and if you have a simple knowledge of math, is going to do nothing. 1 times anything is itself. So it's and actually, so that made me think about what the sort of pattern is going on with the end case. I guess the formal way of thinking of it is just kind of the identity case, in that it does nothing. Like there's a function ID, which I used to think was the most useless function in the entire world, because all ID does is just return the thing. And that's why you can have literally A to A. There's very few functions that are like A to A without any restrictions whatsoever. Because what can you possibly do if you don't know the actual types that you're working with? Actually, there's a couple more functions, come to think of it, that are quite important. But yeah, so there is actually some applications in as we'll get into more complex structures in Haskell. But yeah, so it's really the point, just to drive it home, is that this kind of is the ID case. Yeah, and there's a more formal word for it in Haskell, but it doesn't really make sense here. We already did that. Filter. So filter is going to get us into list comprehension. If you're familiar with Python, there's list comprehension there, and we can do list comprehension here. So I've done a lot of Python, I've done a lot of Haskell. I am biased, and I love Haskell. I'm extremely biased, so I'm going to say that, Haskell is better, but, yeah, it's just, because I like Haskell. So I'm going to call this my predicate, which is a fancy word for, like, does it pass this test? I could call it F, but I won't. So so we're going to use list comprehension here, and the basic structure is kind of this bar in the middle here, and so we're going to say what we want on this side, and so maybe I'll start with this side. So how do I word this? We are saying we want x on this side, so long as, x, where is x coming from? X is from x's, and then we're going to put a comma so that we can also give it a predicate, or use our predicate as a predicate. Yeah. And we are going to say predicate x's. And so what this is saying is this x from x's is the same thing as us peeling off 1 from the list, and then exposing it as x. We're going to run a predicate on x's, or sorry, on x, I mean. And so long as this x passes this predicate gives back true, then we will place the x here and continue on. Yeah. So if we do filter, let's say equal to 1, and by the way, this is technically what's the word I'm looking for? Partially applied, and that there would be some other x here, but this is valid Haskell because for any function we could apply, like for example, I could say filter 1 is a partially applied function, and if I was to ask the type of this, it would give me that filter 1 is of the type A to A. And that's how partial application works, if you're not familiar with that. Here, so that's only going to give me 1. Well, you know what? So I'll just get into anonymous functions. So this is also an anonymous function here, and div mod x. So I am using my anonymous function that I built here on. So I could do the last function like this, where could say x is equal to 1. And now what I want to say here is if x is even. So what's quotient again? Let me just check something quick. No, that doesn't do what I remember. So if I do x div mod x 2, so div mod is going to give me, so if I even just show you guys this first, just in case you didn't see my other lesson, I forget where I use this, right, this is going to give me how many times 2 goes into 5, as well as the remainder of 1. So what I'm going to say here is that for x, div mod 2, so even, div mod x 2, if the remainder is 0, then it is even. So second, you know what, I'm starting to get into some more things that I'm trying to avoid getting to right now. So, you know what, but I will finish off showing you the example of the anonymous function, because I use it so often with filter. Cool. That's how I would do it. I also don't need to do that in this case, because I can just say equal to 1, and that will do the exact same thing. but it doesn't really matter either way. Either way is going to work just as fast. There's a lot that you don't need to worry about in terms of like, you know, what's the right way to do things. They all are going to work exactly just as fast. Haskell's also very efficient, so yeah. But we will get to what I was going to show there. Wait a minute. Sorry, my brain is crapping out. We could have done this. What am I saying? Okay. I thought I had to. Yes, okay. I did not. No, I am dumb. Let me just do this quick. X2. And then if we say second. Yes, that's all we needed to do to begin with. I'm going to say 1 to 10. Oh, right. Right. So 0 equals the remainder. So from the remainder of 2 into x. So this is just basically asking if x is even. Now, if we go do moving on. Now I will get into some more, like as we can kind of get through the basics. I will start to do, more tricks and stuff, I suppose. So we did that. So zip. So in this case, we're dealing with two different lists. So we have list 1, and I guess this doesn't have to. So these lists don't have to be the same type as we were saying with the type signature. A polymorphic can be any type, and B can be any other type. They can even be the same type. If I said A and A, they have to be the same type. I'm enforcing that they're the same type. But here, there is no restriction whatsoever. So, A, B. So here, I have a bit of a unique case, and I'm just going to handle the main case, which is we have X peeled from X's, Y peeled from Y's, and we are going to say X, Y. We're going to build our tuple, right? So this is just a list of tuples. We're going to build a tuple, and then we're going to build a list. Right, so X and Y just being peeled from each list, and that's going to build a new tuple, or a tuple in the new list, and then we continue on recursing X's, Y's. And now we have a bit more complicated edge cases to think about. So what happens if we have we run out of X's? Then it sounds like a good thing, but if we run out of X's, then we just want to end. So we just put the empty list, and this is going to evaluate to being an empty list here. And so in this case, if we only had 1 in the list of X's, we would have 1 tuple at the end. Similarly, if we had that, we would also want to do the exact same thing. So we had 1 Y, or we ran out of Y's before we, ran out of X's. Then, that sounds so, what's the word I'm looking for? Philosophical? I don't know. But, then we just end with the empty list, because although we have more in the other list, there's no logical way in which we can create pairs. And so I don't think we actually, I'm not 100% sure we need to do this. But, well, yeah, I was going to say, what about this case? But looking at it, so this is going to be the first case to be evaluated. This being the second. This would be the third, but I'm not going to do it. And then this would be the fourth, is the third. You get the idea. But since this is kind of generic, this doesn't really pattern match at all. It just says we have all this really is saying is that we have a second argument. It's not even really saying that it has that second argument is a list. This is saying that the second argument is a list because we start to unpack it. But yeah. But because we are pattern matching on this case would be included in that. So yeah. Again, I am just going to, for the sake of keeping things, well, you know what, that's not really. Cool. We see it a value, or compiles. We can test our zip function doing 1 to 5, and let's do 2 to 4. So this makes sense because we take the first from each, and then we're going to run out of, continue on, and then we're going to run out of the 2 to 4 list before we run out of the 1 to 5 list because it is shorter by 2. Okay, so and then that brings us to our last one. So I want to do zip width, just a very similar function, and I'm even going to be lazy, and I'm going to steal this because they are literally the exact same, besides a couple things. Instead of returning what must be a tuple, we are just going to sorry, I'm just realizing that we could have done zip with list, or yeah, with, my brain is blanking out this stuff, this syntax here. But anyways, not important. Again, it does the job. Zip width is just saying that we can return any C. We have another function as well. So long as our types fit together. So this A, of course, corresponding to the list of A, the B corresponding to the list of B, and the return type C being what ends up in C. You know, this will be our. I forget what I was going with that statement. In all honesty, but I think I'm just thinking about the time for this. Wow. Yeah. So. Actually, can we even do this? Yeah. So those still would be the same. But yeah. So I guess the last thing I was going to say is that we are running this function on the same index. So, you know, the first element of each list will be used against the other first element of the list, and so on and so forth. Now, x's, you know what, let's use, well, no, you know what, I'm just gonna, I kind of like this, honestly. I don't even really use the list syntax. Show, and then we have our function f. So I'm going to say that f doesn't even matter in these cases because we're not going to use it. And then we have a function f. So we're going to say f, x, y. That's going to apply f to x and y, which are the same index, and then we are going to recurse with x's, zip with f, x's, and y's. And then we have implemented zip with. We can check that it works, and I'm just going to say hiding zip with because I am lazy. And zip with 1 to 5. Forgot my function. I'm going to add these two together. And I'm going to do 1 to 5 as well so that you can kind of see that it does in fact work. Still can't get away from that, eh? So 1 plus 1 is 2, 2 plus 2 is 4, so on and so forth. And that is all. So, these are, again, some of the most core functions that, are in use in the Data.List library. There's others for sure, but again, there's so many, it wouldn't make sense for me to just simply talk about them. But anyways, I hope you enjoyed, and please, again, let me know if you have any questions, concerns, feedback, comment, yada yada. Please like, share, subscribe, all of that good stuff, and have a good morning, afternoon, or night, whatever the heck it is for you. Peace out.